Hi, so today's video is going to be about differentiating the function x to the power of the modulus of x, so x to the power of the absolute value of x. Before we do this, I guess it's just worth noting that this function x to the mod of x is only defined for x being greater than 0. And again, that's kind of because of why the function x to the power of x is defined for x greater than 0, and it's because you can't really take square roots and fourth roots of negative numbers essentially. So yeah, we've got to make sure that x is greater than 0 for this function to be defined, and therefore its derivative to be defined. So yeah, let's go ahead with the differentiation here. So if you, as you probably guessed, it's going to be a chain rule example essentially. But before we do that, let's just clean up this x to the modulus of x by writing it in a different fashion. And so we're going to write it like this. So e to the power of the natural logarithm of x multiplied by the modulus of x. And then now we can get on with the differentiation using the chain rule. So again, we're going to use the chain rule here. So applying the chain rule formula that we've done in videos before, what we can do is we can say that this derivative is equal to the derivative of this e to the ln x multiplied by the modulus of x, differentiated with respect to the function inside the exponential function, which is this ln x modulus of x, like that, and then multiply that by the derivative of the ln x multiplied by the modulus of x, and then differentiate that with respect to the variable x. Okay, so we get that there. If we just start with this first one on the left-hand side, so this derivative of e to the ln x modulus x with respect to ln x modulus x, well, that's just going to give us the exponential function that we've got there already. So ln x in the power multiplied by modulus of x in the power of the power of that e of that exponential function. So we've got that for the first bit, because that's how we differentiate exponential functions. And then for this second bit here, I mean, this is going to be the product rule, isn't it? So we've got the product of two functions there and there. So we're going to need some product rule. Let me just make a note of that there. This is the product rule. So we know how to differentiate the natural logarithm of x, because we did that before. And the result for that, we just make a note of the results over here. So differentiating ln of x will get us 1 over x. And differentiating the modulus of x, so we did this in a previous video too, so we know that this is just going to be the modulus of x over x, or x over the modulus of x. It's exactly the same thing, so x over mod x is the same as that as well. Great, so we know that. So let's just write this down then using the product rule. So it's the derivative of the first function times by the second function, so 1 over x multiplied by x, and then plus the derivative of the second function multiplied by the first function, so ln of x multiplied by this mod of x over x, like so. So we get that. And then just to tidy things up a little bit, so we know that this e to the ln x multiplied by the modulus of x, well, e to the ln x is just x, because the exponential function and the natural logarithm function are inverse functions. So this is just an x there to the power of modulus x. And this is multiplied by, 1 over x times by x is just the number 1. And then plus this result over here. So the modulus of x over x multiplied by ln of x, like so. So yeah, we get that final result there. We can't really do anything to simplify that. So our final conclusion from this is that when you differentiate, x to the power of the modulus of x, the absolute value of x, you get the result we got back here. So x to the modulus x multiplied by 1, and then plus this modulus of x over x multiplied by the natural logarithm of x, just like what we got down there. And that is the final result for today's video.